Hello everyone, welcome to this lecture on a row echelon form and reduced row echelon form of a matrix. I am Dr. Vikrant Yadav, Assistant Professor in Department of Mathematics at SR University Warangal. Today we are going to discuss two important concepts from linear algebra which are used extensively in solving system of linear equations. Whenever we have multiple equations and multiple unknowns, solving them directly can become very complicated. Matrices provide a systematic and efficient way to represent and solve such systems. Two such powerful matrix forms help us do this, which are row echelon form, that is we call as REF, and second is reduced row echelon form, that we call as RREF. These forms simplify matrices using special operations called elementary row operations. By the end of this lecture, you will clearly understand what is REF, what is RREF, and how to convert a matrix into these forms, how to interpret the solutions of linear systems using these forms, and also how REF and RREF are connected to concepts like rank and invertibility. So let us begin. Before we start, let us quickly see the outline of today's lecture. Part 1, that is REF or row echelon form, in which we are going to see the elementary row operations, the definition of row echelon form, and some solved examples. Okay. Part 2 is reduced row echelon form, in which we will see the definition of RREF, that is a reduced row echelon form, and some examples in which we convert row echelon form into reduced row echelon form. After that, we will also see the types of solutions, that is unique and infinite solutions and no solution. Okay, whether the system is consistent or not. Finally, we will see the comparison between REF and RREF. And at the end, we'll be seeing like some important applications and theorems. Okay. Now, the first concept we must understand is elementary row operations, because these operations are the tools we use to transform matrices. Whenever we solve a system of linear equations using matrices, we usually write the system in the form of augmented matrix. For example, 2x plus y minus z equal to 5 and x plus 3y plus 2z equal to 7. Okay, we can represent these two equations, with the help of matrices. But solving them directly from matrices is not that much easy as it seems like. So we'll simplify the matrix using elementary row transformations. Okay. There are three types of row operations which we use to just transform the matrix, okay, without changing the solution set. Type 1 is swapping of two rows. That means the row ith row can be interchanged or swapped with jth row. I can write the ith row in place of jth row and jth row in place of ith row. Okay, this is useful when we want to move a non-zero element into a pivot position. Okay, next is row scaling. That is when we can multiply a row by any non-zero constant. That is, for example, Ri multiplied with k. So it doesn't change the solution basically. This helps us create pivots equal to 1. Next one is row replacement, in which we replace ith row with ith row with a combination of itself and another row. For example, it is written over here Ri equal to Ri plus k times Rj. Okay, this operation is extremely useful for eliminating elements below and above pivots. These three operations form a foundation of Gaussian elimination, which we will be seeing later on. Using them, we can transform matrices step by step until they reach row echelon form. Okay, that is the main point here. Next is the definition of row echelon form, that is REF. Okay, let us see what it actually means. A matrix is said to be in row echelon form if it satisfies the following three conditions. Okay, if the any matrix satisfying these conditions will said to be in row echelon form. A matrix is in row echelon form. Condition 1, all the rows consisting entirely of zeros appear at the bottom of the matrix. Okay, then this will ensure that the matrix structure is well organized. Okay, matrix structure is well organized. Then condition 2 is there. It says that the first non-zero entry of each row, that we usually call as pivot entry, should appear to the right of the first non-zero entry in the row above it. Okay, this is second point. And the third one is, and also in the second point itself, this will create a staircase like structure. That is why we sometimes call the REF as staircase form, or the REF is also known as staircase form. That means it creates a structure like this. Okay, a staircase like structure. Now, condition 3, all entries below each pivot entry should be 0. Now, you will say, what is pivot entry? Up here again, as I have already told you, pivot entry means the first non-zero entry in any row. Okay, so a pivot is the first non-zero entry in a row. Correct? It is the first non-zero entry in a row. Okay, and the column containing that pivot entry is called the pivot column. And columns without pivots are called the free variables. They will give the free variables. Okay, so this is the structure which gives the general shape of REF. These entries in square boxes, solid boxes, are the pivot entries. Below them we are having all the elements as 0. Okay, these are 0 only, and these are free variables without pivots. Okay, now we shall try to understand this concept in more detail. Okay, so here we are given a 3 cross 3 matrix. Okay, square matrix. Our goal is to just transform this matrix into row echelon form, that is REF. This process involves eliminating numbers below the pivot positions. So let us start. First we choose the pivot in the first column. Okay, that is, say, if necessary we will swap the rows so that a convenient pivot appears at the top. Okay, now what do you mean by that? Say we choose this one to be here. So we are just swapping it for our convenience. We can continue with 2 as well as the first pivot entry. Okay. So after swapping the rows in step 1, I got this kind of matrix. That is, I wrote second row. that is 1 3 2 at the first place, first in place of first row, and second row in place of second, I wrote the first one. Okay, so our first pivot entry is 1 in step 1. Okay, the first pivot entry in column 1. Okay, now our next target is to just make 0 below this using this row 1. Okay, so let us try it. We will eliminate the entries below the pivot using a row replacement or row transformations. This means we subtract multiples of the first row from other rows. Okay, so we have applied the operations like R2. It was having 2 here, so we applied the operation R2 minus 2 times R1, which changed the second row as 0, minus 2, and minus 6. At the same time, we applied the operation on row 3, that is R3, with the that operation is R3 changed to R3 minus 3R1. It changes to 0 and 0 here below this first pivot entry. Okay, then after that we go to the second pivot in the second column. Okay, that is in the next column, that is in the next row. Okay, that is equal to minus 2, first non-zero entry in the second row. This is second pivot entry, minus 2. With the help of this minus 1, we need to make 0 below it. Okay, so we applied the operation. That is very simple to understand, that to make minus 4 equal to 0, we need to subtract 2 times of row 2. Okay, so finally after the application of this operation, that is row 3 minus 2 times row 2, we got the matrix like this one. Okay, here two pivots are there, that is 1 and minus 2. After that, the rank will be equal to 2 here. The concept of rank will be discussed in a separate video. Okay, for now you just understand that number of pivot entries is rank of the matrix. Okay, and there is one free variable. This column is free now. Third column is free. Okay, free means you can call it like if you're having two pivot, it is 3 cross 3 matrix. There are two pivot entries. That means two rows are uh, independent, and this one is dependent. That we call as free variable. Okay, so let us continue to the next slide. So let us take one more example related to a row echelon form. Okay, this time I have considered an augmented matrix representing a system of linear equations. Okay, that is augmented matrix, and we are required to convert it into row echelon form. The steps will be same. First, go to the row number 1 and then choose the first non-zero entry. But here you can see that the first non-zero and it is zero entry here. So for our convenience, we just interchange row 1 and row 2 so that it becomes in step 1, that is, as you can see on the screen, that is 1 1 minus 1. This is the first row along with 2 as part of augmented matrix, and the other two rows are there. Okay, then you are required to convert and you are required to choose the first non-zero entry in the first row. Just understand that swapping of rows or any other row operation we are applying, that won't change the solution of this system of linear equations. Okay, or any other system of linear equations. So let us see, just look at it. Now 1 is the pivot entry. Here is automatically 0. and in the third row at first place, that is 2. So we are required to make this 2 equal to 0. So I simply applied the operation, that is row 3 changed to 2 times minus 2 times R1. So it makes 0 at both the places in the first column. Now this is the second row. Next is to choose the second pivot in the next row. First non-zero entry in the next row. That is true here. So I choose it like with the help of this true, I need to make 0 here. Okay. So I wrote the operation like row 3 changed to row 3 plus 3 by 2 R2. This will definitely make 0 here. Okay. Here at this place. So we have gotten 0 here as well. Now I go to the third row. Okay. Third row is having first non-zero entry at this place, that is equal to 9. Correct. So this is our pivot entry and we need to make 0 below this, but no elements, no rows are there below this. So it is the third pivot entry. Okay. The pivot entries are 1, 2 and 9. Okay. But since it is an augmented matrix, so we can substitute back these values to get the values of x1 as 1, x2 as 2, x3 as 1. So this system of linear equations is having a unique solution. Okay, how do you solve that? You just back substitute it. That is, last equation I'm writing 9x3 equal to 9. Okay, that will give you x3 equal to 1. Similar way, second equation is 2x2 plus 4x3 equal to 8. Here I am already having the value of x1, replace it here, I get the value of x2. Similar way you can get the value of x1 as well. Okay, and that is all in this example. So let us take one more example of the order 4 cross 4. That is a matrix of order 4 cross 4. So in this, we will choose the first non-zero entry. That is the pivot in the first column. Okay, and make 0 below it, 1 by 1. Below it. Okay, this will be 0, this will be 0, and this will be 0. So we'll just apply suitable operations like R2 change to R2 minus 2R1, R3 change to 4 times R1, and the R4 is automatically having 0 here, so we need not to apply any operation here. Okay, so after applying these two operations on row 2 and row 3, we get the matrix as you can see on the screen. Now we go to the next row. Okay, in next row, row number 2, we choose the first non-zero entry, that is 1 here, and with the help of this one we are supposed to make 0 here and here. Okay, rules will be same, we are applying the same operations. Now in step 2 we applied the operation as row 3 changed to row 3 plus 2 times row 2, and R4 changed to R4 minus R2. That will make 0 here at this place and this place. Okay, now again to row 3 to choose the next pivot, and that is again equal to 1 here, first non-zero entry in the matrix. So it will become, actually we are having 0 already here, right? So we need not to change it. So then we go to the next row, that is row number 4. Okay, choose the first non-zero entry, and that is equal to minus 3, and this is your first, this is your required row echelon form for this 4 cross 4 order matrix. Okay, there are 4 pivot entries, and that is equal to the rank. Okay, that is equal to the rank. So Since we are having 4 pivots and 4 order of the matrix is also 4, a square matrix, therefore we have a unique solution for this system. Might be okay, and the matrix is invertible. Okay, if for a given matrix we can find the inverse, there is a square matrix only. Okay, if it is invertible or determinant of it is non-zero, if suppose determinant A equal to this is not equal to 0, that is known as non-singular matrix. Okay, in that case we have unique solution that will exist for that given system of linear equations. Okay, so I hope you are able to understand what I am trying to teach. So now let us move to the definition of RREF, that is reduced row echelon form. It is simply a more refined version of row echelon form. Okay, a matrix in RREF, it will be there in RREF if it satisfies all conditions of row echelon form. Okay, and plus two additional conditions. Okay, now let us know about these two conditions in detail. First condition is each pivot must be equal to 1. If it is not 1, we need to make it 1, okay, by applying suitable row operations. Next, every entry above and below each pivot must be 0. Okay, I mean every entry above and below each pivot must be 0. This means the pivot columns basically look exactly like the columns of the identity matrix. Okay, it's like see in this general shape of RREF, this is the first pivot entry. Okay, so below this are all 0. This is the second pivot entry, so above it and below it both should be 0 only. This is your free variables. This column is in these variable, these two entries are free column, and these are equal to free columns. Okay, now an important property of RREF is every matrix has a unique, very important, every matrix has a unique RREF, and the method used to reach RREF is called Gauss-Jordan elimination. Okay, that we call as Gauss-Jordan elimination method. Correct. After that, REF, if we are having a matrix in row echelon form, we eliminate we eliminate the entries above pivots, make them 1, then we reach up to row echelon form, reduced row echelon form basically. Okay, I hope you're getting it well, so try to focus and work on it. Okay, now here we start with a matrix already in row echelon form, that is example 1 of row echelon form. This is there which we saw in the examples of row echelon form. Okay, now we continue the process to reach reduced row echelon form from here. Okay, first we scale the rows so that pivots become 1. Clear? So that pivots become 1. So the two pivot entries are here, that is 1 and -2. We need not to change this one, but we need to make this entry -2 as 1. So let me multiply with minus half. Row number 2 I am multiplying with minus half, so that it becomes in this form after step 1. Okay, after this then the pivot entries are equal to 1 basically. Now I use these two pivots to make 0 above this and above this one. Okay, means the entries are existing in pivot entries are existing column 1 and column 2. There we need to change every entry except this pivot is equal to 0. Okay. How can we do that? We can simply eliminate, say in column 1 there is no entry above this one, so we need not to change it. But in this second column we are having this entry equal to 3. Okay. How can we convert this 3 in the pivot column only? We need to make changes, right? So row 1, I'll apply this operation. Row 1 change to row 1 minus 3 times R2. So it becomes, first row becomes 1 0 minus 7. Second row is automatically 0 1 3, and this is 0. Okay. So this form is your RREF. Okay. This form is RREF, and RREF is basically some sort of extension of REF only, because we will reach RREF only when we have some row echelon form of the matrix. Okay. And in this case we are able to see that this there is one free variable, that is this last column is free now. So therefore we are having the solution of the type this, and let x3 equal to t and x1 equal to 70 will get from it. Okay, because this is free. Okay, solving these two from this step, if I try to solve, I'll be writing the equation as x2 plus 3 times x3, right? That kind of we can solve if the right hand side part is given. Okay, I hope you are getting it. Stay here only. So this is example number 2 for RREF. In this example, we again convert the row echelon form, okay, into reduced row echelon form. First, we scale rows to obtain pivots equal to 1. Say here the pivot entry is 2, here it is 1. 1 is okay, but 2 should be made equal to 1, and here it is 9. Okay. So let us convert them first into 1 and 1, each pivot entry equal to 1 here. So we are getting here after the application of the row operations like row 3 change to 1 by 9, row 3, and row 2 change to 1 by 2, row 2. Okay. So after that, in step 1, we are getting this kind of matrix. From augmented matrix basically it is. In step 2, we are getting this row 2, means we are going to change, we are going to make 0 above all the pivot entries. Okay, above all the pivot entries. So I applied the operation row 2 change to row 2 minus 2r2. Correct. I'll be applying the operations beginning from the end, this one last pivot entry. So this will become 0. Now in the next one I'll be applying the pivot operation as considering this one, okay, and get the value here 0, right? So the rank here is equal to 3. No free no free variables are there, correct? Because it is an augmented matrix. Okay, so no free variables are here, so we have gotten the solution directly, and that will be equal to x1 equal to 1, x2 equal to 1, 2, x equal to 1. This one is this one, this will go to 2, this one will go to this one. Okay, so this is how we solve or we convert row echelon form into reduced row echelon form, or we can directly start from row echelon that any given matrix and convert that into first row echelon form and then reduced row echelon form. Okay, now let us compare REF and RREF. Okay, in REF we are having, that is row echelon form, we are having the pivots that may be any non-zero number. Okay, it may be any non-zero number. Second, only entries below pivots are 0. Above them may or may not be 0. Okay. Now we can get the solution by back substitution. Okay. And the row echelon form of any matrix is not unique. We may have several row echelon forms. Okay. But in RREF, as you can see, the pivots always are having the value equal to 1. Okay. And trees above and below pivots are all 0. Solution can be read off from directly from this row echelon form, reduced row echelon form, and also it is unique for any matrix. It will be unique. Okay, no other reduced row echelon form or RREF can be calculated. Okay, then we are having this. There's a key relationship between RREF and REF. Basically, if you are having reduced row echelon form, that is simply REF also, but not all REF are RREF. Okay, we can get REF by Gaussian elimination. Okay, we can get REF by Gaussian elimination, but RREF can only be obtained from Gauss-Jordan elimination. Right? So, these matrix forms are extremely important in many areas. For example, rank of a matrix. Okay, the rank equals to the number of pivot columns in REF or RREF form. Okay, this is rank nullity theorem, which states that a rank of a given matrix plus nullity of a given matrix is equals to n, where n is the number of columns. So this is the most fundamental theorem in linear algebra that we'll be seeing in the later on videos. Okay, and then there is second application like consistency theorem, which states that our system is consistent if there is no row like this one. For example, you are having a matrix like here entities are there, but there is some row like 0, 0, 0, then augmented C means there is some row, okay, like of this form, where C is not equal to 0. In that case, the system is having no solution, correct? Then we have another application like unique solutions will be there only when pivots, right? Pivots equal to the unknowns, no free variables. Number of pivots is equal to the number of unknowns. So it's very important. Okay, if there are three pivot entries and number of unknowns is also there is variables is also three, so we'll be getting a unique solution. If free variables exist, then we get infinitely many solutions. It means that if suppose that the number of pivots is 2 but the unknowns are 3, so we will get infinitely many solutions. Okay, and that one variable that is free, okay, that will be responsible for so many infinitely many solutions. Okay, then at the end we have no solution and the system is said to be inconsistent in that case, correct? Just like I discussed here in this case of this, where the one row is completely zero and it is equal to some constant or anything like that. The last one is matrix invertibility. Any matrix of order n cross n, that is square matrix of order n, is invertible if and only if its RREF is identity matrix. Okay, if RREF is identity matrix. Okay, so these are the fundamentals and some basic concepts related to row echelon form and reduced row echelon form. So Okay. So thank you for watching this lecture. I hope this video helped you clearly understand row echelon form and reduced row echelon form. If you found this lecture useful, like this video, share it with your classmates, subscribe for more lectures on mathematics and linear algebra. Thank you and see you in the next lecture.